So welcome back. In lecture 12, we are going to discuss some important issues related to underfitting, overfitting, and how can we best fit our data using linear regression model. And then I am planning to tell you the story of statistical interpretation of linear regression model. So let us start with these simple examples. You see, say we have some data which is visible, and ignoring the trend of the data, I have fit a hypothesis h parameters by w of x equals to w0 x0 plus w1 x1 is a straight line. So basically what we have done, we have incorporated less than required parameters. Okay. And then what will happen? So this is a perfect example of underfitting. And if you just, your data trend is this, and if you are just fitting this line, then after regression, this line obviously will fail to predict. So it will be useless and very bad design, right? So this kind of problem we call high bias, low variance, okay, problem. Now, don't worry about this terminology. We'll discuss them many times afterwards also. But basically, high bias means these are now statistical words. In this context of fitting, the high bias means I have used less number of parameters, and basically I am biased about, okay, I think that this is a straight line. Okay, if you do that, then this design will have low variance, means it will be very rigid, and it will fail to predict the environment. On the contrary, I have this sample, and then I have decided to design a hypothesis incorporating many parameters. Okay. Say for example, w0 x0 plus w1 x plus w2 x square plus w3 x cube plus w3 x to the power 4 plus w5 x to the power 5 plus w6 x to the power 6. So many parameters I have incorporated in my predicted design with the intention that the curve will fit the training data the best. I think the best, right? Because my curve is passing almost through all the sample points. So this is called, this is also a problematic. Why? Because it will fail to generalize, because my design should not be confined in this design data zone or training data zone. It should be able to predict the data beyond that, and it will miserably fail there because it could not generalize. And this problem is called overfitting problem, and essentially this has high variance. Variations are very high for incorporating so many parameters which are not needed for this kind of samples. So we will have high variance, and low bias means we are very fair. No biasness is there. We intended to pass our line through all the samples. Okay, and this, so both of them are bad, whereas the best fitting could be this one, w0 w hwx equals to w0 x0 plus w1 x plus w2 x square, because the nature of the quadratic nature of the sample. So I have able to design the predictor accordingly, and that will be the best fit, because as long as this nature of the data remains, my predictor will be able to predict. Okay, that's why we are calling it best fit. Now, how do I know that sometimes the visualization of the data is not possible? How do I know that this will be quadratic, this will be linear? Okay, so using some control over this parameter W's, we would like to solve the problem of underfitting and overfitting, and we intend to make our predictor best fit our sample data. And this technique is called regularization. Okay, this is a very, very important concept, and I will try to make you understand um, with simplicity as possible. So this is our JW is our cost function, right? And nature of the cost function was 1 by 2m summation of I equals to 1 to m sample. This for m sample. This is my HW, XI is the sample minus YI is the level squared. So this was our very well known, very many times seen cost function. Now we are adding some lambda j and summation of j equals to 1 to n wj's squared. Okay, so this is incidentally called regularizer term. So this is called uh, regularizer term. Okay, so why we did that? Let us try to understand. And now first of all, one issue is lambda is a parameter. Actually, this is a hyperparameter. Again, you have seen one hyperparameter learning rate alpha, okay, which was actually regulating or controlling the derivative term of the cost function. And here we have introduced another hyperparameter, lambda. These parameters, they are called hyperparameter because they control the parameter. Okay, uh, so they are that's why they are called hyperparameters. And J normally we do not regularize lambda 1, lambda 2. We do not attach hyperparameter for each parameter. Instead, the value remains same. Okay, it's kept constant. That's why J I am omitting. Now, why? What is the basis of just bringing this term? We'll try to understand. Now, uh, our objective was to design a hypothesis which will best fit our samples. Okay. Now, for that best fit, we have seen that as many parameters are there, uh, there will be fitting. Okay, it may be overfit. So why not to keep the importance of these features x square, x cube, higher order feature term by making appropriate parameter attached to it, and let them this parameter um, value, let there be very, very small and be regulated, okay, by attaching a lambda to this parameter w, so that um, the the lambda will have high value if required, and then this will be very, very low values. The parameter will have very, very low values, okay, like 0.02, 0.002, okay. And in doing so, we are trying to understand that, okay, our intention was to keep as many parameters are needed, and let the regulator either discard it or accept it, okay, by attaching appropriate values, okay, which is we are attaching appropriate values to hyperparameter lambda, okay, so which is controlling the parameter value. So this is actually the reason, and why again we have squared it. you all know that we have squared it because the cost function, we need to make derivative of the cost function. Okay, the cost function is squared. So here that's why we have made wj squared. Okay, and attaching a regularization parameter, hyperparameter lambda. So that is the basis of regularization. Okay, so it's as simple as this. Try to keep as many parameters as needed, because as you can see, the best fit the sample, and make them also generalize by keeping those parameters very small. Okay, and in incorporating that in my cost function actually allows me to determine the wj as required. Okay, so this is the issue. So now if you just so this is my new objective function, and I'll have to differentiate it with respect to j, which we have done it here. Okay, let us call it this is question number 1, and this is question number 2, which we are going to use. Okay, so this is a derivative of this function. Okay, and now let us run GDA, and that will take care of that will take care of the control of the parameter. See how. First of all, this is the first parameter W0, which is always attached with a fictitious feature X0, which is always made 1. So that's why we do not need to, because this is not attached to the feature. Okay, we do not need to regularize this term. Okay, so no regularization is required. That's why we have kept as it is. No regularization is required on this parameter, because it is attached with a fictitious feature, no real feature. Okay, so others are real features. Okay, so wj j equals to 1 to n number of features we have taken, so that is equals to wj, that is assigned wj equals to earlier wj minus this is, you have already seen it. The GDA has now another, the updation, weight update, parameter updation has another term. Okay, which is which has come, you see here. Okay, this has come 1 by 2 m lambda by okay 1 by 2, this 2 cancels out, so lambda by m remains. Okay, and that is the term. So, and alpha times lambda m wj, and this wj and this wj now this factor is common. Okay, 1 minus alpha lambda by n times wj minus this is the um, derivative of the cost function, usual cost function without regularization term. So what regularization term is doing, it is keeping a control with the parameter itself. Alpha was keeping a control over the how much is a learning rate, how much updation will be done. That is the control, okay, of alpha. How much deduction has to be made with the parameter wj. Now wj is also regularized with this parameter, and see the nature of the parameter. Normally m is large, we are talking about million sample. Okay, and alpha is 0.01, say is small. So this term is much less than 1. Okay, so it's much less than 1. So what is happening during the process of gradient descent algorithm running, actually the parameter itself is having a sinking effect due to the addition of the regularizers. Okay, and this shrinking effect meticulously try to adjust the parameters. Okay, that is the advantage which regularizer is giving. So you can argue that how to determine the lambda parameter. Okay, lambda parameter has to be, many researchers have done some research, is a value maybe 1000, 2000, whatever. So you design it, you attach that value. It's a design, right? And then attach that value and get your parameters, get your hypothesis design, and then in the testing phase, test it whether it is better than without regularization. Okay, you will have to see. And if you want a better prediction, so then again come back and then again redesign lambda, and this is an iterative process which will help you to tune appropriately the hyperparameter values so that your design of predictor becomes sound, that can be tested, okay, by getting better um, prediction rate. Okay, so let us now see um, what effect this regularizer has on our normal equation form of linear regression. So if you see that in the lecture number 8, we have deduced the normal form of equation. This is in matrix form, okay, where um, this x, that is the feature vector, okay, has a dimension n plus 1 cross n plus 1. Okay, this is a dimension of n plus 1, n plus 1, and then you need to invert that, and then x bar transpose times the level, okay, level vector. So this was our, directly we are getting W. And you have seen the basic problem we had there was non-invertibility of this matrix, isn't it? And whenever there was any row or column repeated in nature, okay, then the determinant of this matrix um, were actually becoming 0, and the inversion was non-existent, right? Now, if here we add a regularizer term, okay, so this is the dimension of this, this matrix has a dimension n plus 1, n plus cross n plus 1, okay, and this has the x bar has a dimension m cross n plus 1, y has a dimension m cross 1, okay. So this regularizer also has to be in the dimension of n plus 1 cross n plus 1, and since we do not regularize the first term, so we have kept everything as a 0 row, okay, and then for first term we have 0 only, this is 1 and all others are 0. For second term, we have 0, 0, 1, all others are 0. Third term, we have 0, 0, 0, 1, and all others are 0. Like this, it has n plus 1 column, and it has n plus 1 row. Okay, so we have added this times a lambda value which we have given, and then we are determining W. Okay, so idea is clear. So this is regularized matrix we have incorporated in our matrix form of normal form of equation. Okay, giving a value of lambda. So as long as lambda is not 0, okay. So as long as by the as long as if lambda is greater than 0, okay, then we observe, please observe that this regularizer term is ensuring that the determinant of this matrix will never be 0, because the 0 plus non-zero lambda times something is there, right? So And this is a problem, you see, especially when number of samples, and this is a number of features, number of samples are very, very less than the number of feature, less than equal to number of feature, then you will definitely get some rows which are dependent, and the non-invertibility issue are there. You could not use this, but adding simply a regularizer term, you could actually use the normal form of equation. Okay, so this is what we wanted to convey, that the regularizer has a great effect in actually making the parameter designing and tuning more practical and more effective. Okay, so you will get some assignments also using regularizer, and let you play around and decide what will be the hyperparameter value. Okay, so you try to design parameters without regularizers and with regularizer, and see whether classification rate have improved or not. Okay, so that will give you the basic idea of regularization. Okay, what is very, very important, and always we regularize. Okay, for designing effectively the parameters and the predictor. So with this, I would like to take you to the next class. I would like to discuss something about the probabilistic interpretation of linear regression model. Till then, stay safe. Bye bye.